Alright, so this is where we left off yesterday. So we have energy transfer between systems. So two systems at different temperatures that are in contact with one another will exchange heat, right? We said yesterday they exchange heat by conduction, which is contact. And you can see here system 1 is the lower temperature system because the vectors are smaller. System 2 is the higher energies or higher temperature system because your vectors are much larger. Energy transfers when these particles collide with the barrier, okay? And that's what makes it heat transfer by conduction. Okay, so your energy is transferred from system 2 into system 1. Eventually they reach equilibrium where both systems are at the same final temperature. It's important to remember that all of the energy that gets lost by system 2 is gained by system 1, right? And that's our conservation of energy. So we talk about conservation of energy as energy cannot be created or destroyed, right? But it can be transformed into different types. So energy of a system generally changes because of a chemical reaction, a phase change, a change in temperature, right? All of these things can result in energy being transferred into or out of the system in the form of heat or in the form of work. Okay, so conservation of energy, generally your energy changes into heat or it changes into some type of work, right? And work is a physics term, which we'll talk about in just a minute in relation to our material. Alright, so when we talk about thermodynamics, we always refer to two things, the system and the surroundings. When we talk thermodynamics, those are the only two things that actually exist. So your system is the chemical reaction taking place, and your surroundings is everything else. Okay, so the actual reaction taking place. So let's say you're mixing sodium hydroxide and hydrochloric acid, right, in a beaker. Okay, the hydrogen or the sodium hydroxide and the HCl, that's your system. Everything else, the beaker that it's in, the air around it, if you have to heat it to make the reaction go, this one you don't, but in some cases you do. Everything else, that's considered your surroundings. So the beaker, the air, heat, everything else, that's your surroundings. Only the things taking place in the chemical reaction, that's your system, right? Even the water, both of these are aqueous solutions, right? They're both taking place in water. Even the water in the beaker is part of the surroundings, right? Because the water is not taking place in the actual chemical reaction. Okay? When we talk about the change in the system's internal energy, that energy is a change in the potential energy and the kinetic energy of the particles, right? We said the change in the kinetic energy relates to temperature. So we talk about the internal energy as the total energy, right? And that delta means change. It's change in potential energy and kinetic energy. Our delta E is equal to potential energy plus kinetic energy of a system, right? Molecules and particles have both. So if you're increasing the kinetic energy, the potential energy must be decreasing. Okay, so delta E is a change in the energy of our system. Q is our heat, right? Heat that's transferred into the system gives us a positive value. Heat that's transferred out of the system gives us a negative value for Q. Okay, and then W is our work done on the system. Okay, so work done on the system by the surroundings would be a positive value. So energy is flowing into the system. So it's done on the system by the surroundings. Energy is flowing from the surroundings into the system, gives us a positive value for work. Okay, or work done on the surroundings by the system gives us a negative value. Okay, so as energy flows out of the system into the surroundings, that gives us a negative value. And that tells us that the system is doing work on the surroundings. Okay, work in chemistry terms generally is the result of a change in the volume of a gas. So we just finished talking about the ideal gas laws. So work results from changes in volume. So we just did an experiment, we just did equations and work dealing with change in volume of a gas, so that relates really nicely to our ideal gas law. Okay, then we have heat and endothermic processes. So if we have an isolated system, right, which means energy is conserved within that system, heat doesn't escape and matter doesn't escape from an isolated system. Our system is methanol, right, methanol gas, and it's decomposing into carbon monoxide and hydrogen gas. Okay, a decomposition reaction, it has a delta H of positive 90.7. Okay, so what's happening here is the bonds in the products contain more energy, more potential energy. The product molecules must contain less kinetic energy. Okay, so these bonds have higher potential energy. So this is why the products of an endothermic, and that information you can get from a table, a data table. This is why the products of an endothermic reaction are at a lower temperature. So whenever if you think about endothermic reactions, they feel cold to the touch. And that's because your reaction is it's taking in heat from the surroundings. So if we go back to our slide over here, if we're transferring heat into the system, we're pulling heat from our surroundings. We have a positive value for Q, right? A positive value for our delta H. That means we're pulling heat from our surroundings into our system. Okay, and that's what's happening here when methanol decomposes. Okay, so this tells us that the bonds in the products, because it's a positive delta H, it tells us the bonds in the products contain more potential energy, which means that by definition, the products contain less kinetic energy. And remember, kinetic energy is related to heat. So lower kinetic energy feels colder. Okay, so if we're still in our endothermic process, because the products are at a lower temperature than the surroundings, the heat is flowing from the surroundings into the system. Okay, heat flows from the surroundings into the system until you reach that thermodynamic equilibrium, that thermal equilibrium. Okay, so what happens is that all of this energy that gets absorbed ends up locked between the bonds, the CO bonds, and those H2 bonds. All the energy that gets taken in gets locked up in the bonds of the products. Okay, so we always talk about endothermic and exothermic in the direction of heat flow. So heat flows, cold doesn't flow. We always talk about our surroundings in terms of heat flow. So if an endothermic reaction happens, it's pulling heat from the surroundings into the system, right? It's not that the system is bringing in cold, right, or it's giving off cold. It's that the system is pulling in heat. The system doesn't give off cold, it pulls in heat, it absorbs heat. Okay, so we always talk about our system and our surroundings in terms of heat flow and heat transfer. Okay, if we talk about heat as an exothermic process, we have an isolated system, right? So energy is conserved, energy doesn't escape, and matter doesn't escape. So we have an isolated system. In an exothermic system, we have our CH4 and our oxygen gas, and we have carbon dioxide and water. Okay, this one we are rearranging our molecules. This one it starts out with low kinetic energy, so it's a relatively cold reaction. All of our energy, high potential energy, so all of our energy is locked up in that oxygen double bond, right? We know that O2 is an oxygen-oxygen double bond, and that CH4, those are carbon or hydrogen bonds. Those are very high energy bonds. So all of our energy is locked up in these bonds. When those bonds break and we form CO2 and H2O, those molecules are much warmer. They have much more kinetic energy. They're moving a lot faster. And these bonds don't have as much potential energy. So our potential energy shrinks and our kinetic energy increases, right? An increase in kinetic energy is related to temperature, which is why exothermic processes feel warm to the touch. Okay, so as the bonds in the products contain less potential energy, the product molecules contain more kinetic energy, so they're moving much faster. Okay, so this is why products of an exothermic reaction have a higher temperature. Okay, and remember, we talk about heat and exothermic processes in terms of energy flow. So in this case, in terms of heat flow, because the products are at a higher temperature than the surroundings, the heat must transfer from the system into the surroundings in order to reach that thermal equilibrium. Okay, so remember again, we're not saying that the surroundings are, colder. We talk about it in terms of heat. So the system is losing heat to the surroundings, which is the definition of an exothermic process. So if we look at this, so this is the change in energy in terms of heat. Now if we look at the change in energy in terms of work, so if we go back to our endothermic process, so we have, remember we said work is caused by the change in volume of a gas. Okay, generally change in volume of a gas. So here we have the pressure caused by gas particles colliding with a piston on the outside of a cylinder. It's greater than on the inside of a cylinder. The gas outside does work on the piston, right? So if you have particles colliding on top, particles colliding inside, notice the size of your vectors. So the vectors are larger inside than they are outside, which means the pressure inside is greater. If your molecules on the outside of the piston start to exert pressure on, right, this is your piston, this black box is your piston. If they start to exert pressure pushing down, then the gas particles inside are going to be compressed. Remember, only gases are compressible, but liquids and solids both are not compressible. So we say that the gas outside does work on the piston as that volume decreases, right? We talk about it in terms of the change in distance. We know, in fact, it's the change in volume. So if the piston is compressed, we know the area of the piston. We can figure out the volume that the gas is actually compressed. Okay, so the gas outside does work on the piston. Energy is transferred from the gas to the piston, and the gas inside the cylinder actually contracts. Okay, so in an endothermic process, your volume decreases. Okay, because the system or the surroundings are doing work on the system. Right, the gas inside of the piston, or inside of the piston, inside of the cylinder rather. The gas inside of the cylinder being your system, the gas outside of the cylinder being your surroundings. Your surroundings doing work on the system, compressing the system, makes it an endothermic process. If we talk about work in terms of an exothermic process, you have the opposite. Okay, you have low pressure inside your cylinder. The gas particles inside are pushing against this piston, colliding with the piston. It pushes the piston up, right? So now your system, the gas particles inside your system, are doing work on your surroundings. The volume of your system increases, and that's an exothermic process. Your system is doing work on the surroundings. Okay, so the gas inside the cylinder expands. The volume inside the cylinder increases. So that's your system doing work on your surroundings. Okay, if we look at that in terms of the math, transfer of energy through work always associated with the change in the volume of a gas. So our work is equal to force times the distance that our piston moves. Okay, and we know that pressure is equal to, or that work then, if work is equal to force times the distance, pressure is equal to the force applied divided by the area that it's applied to. Work then is equal to pressure times area times your change in distance. But however, volume is equal to your area times your distance. Okay, So work is equal to the pressure times the area times that change in distance. Now volume is equal to area times that change in distance. So then we can substitute further, work is equal to pressure times your change in volume. So this is the derivation for work and how work is associated to your change in volume. Okay, you have to have this negative sign. Remember, when we talk about work, it's work in relation to the systems and the surroundings. Okay, it's work in relation to the system and the surroundings. So you have to have that negative value, you have to have negative P times the change in volume in order to get the correct sign for work. So if we go back to our equation here, the change in energy is equal to the heat plus work. So when we're talking about the work done on a system by the surroundings, or work done on the surroundings by the system, you have to have a negative value times the change in volume in order to get the correct sign to plug into this equation here. Okay, and that's because delta V is positive when the volume increases, and delta V is negative when the volume decreases. But we know that work is negative exothermic when the volume is increasing, right? That's what we said here. So when the volume increases, work is negative. So we have to have that negative sign so that it's a negative work, right? Work being done from the system on the surroundings in order to have that change here be correct. Okay, the last thing I'm going to pull these back. Okay, I want you to use, there we go. I want you to use the equation that we just talked about to try these two problems. And then when you're done, work on the practice problem pool questions on the board. Complete those for homework. We'll go over those on Monday. All right, have a great weekend. We'll see you on Monday.